In this lesson, we're going to look at hydrocarbon derivatives and the functional groups that they contain. So, although all organic compounds are made primarily from the same atoms, mostly carbon and hydrogen, but also oxygen and nitrogen and a few others, they have very diverse functions, and this is because they have what are called functional groups within them. And those functional groups give them characteristic chemical properties. So a functional group is just a small group of atoms that are bonded in a certain way, and they're contained within a larger molecule, and then they impart certain properties to the molecule. So you've already been introduced to two functional groups, the alkene and the alkyne. Okay, so the hydrocarbons that contain those functional groups are part of the aliphatics. They're still only carbon and hydrogen. When we start adding other functional groups, which will start containing different atoms, we get the hydrocarbon derivatives. So these molecules have a hydrocarbon, but then they will have a functional group as well, and maybe several. So we're going to talk about each of the functional groups and what they look like and what characteristics they will give to the molecule. So the first one is the hydroxyl group. Okay, so you'll see the groups represented in this way where you've got an R, and R just represents any hydrocarbon chain. So there could be anything over here. What you're looking for is this single bonded to an OH. Okay, so the hydroxyl group consists of an oxygen that is single bonded to a hydrogen. And when there are hydroxyl groups present, we get the alcohol group of hydrocarbon derivatives. And alcohols can also be subclassified according to the type of carbon that hydroxyl group is attached to. So in this situation, we have a hydroxyl group, it's attached to a carbon, and then this carbon is attached to at least two hydrogens, maybe three, but at most, it is only attached to one carbon on this side. Okay, and in that situation, it's what's called a primary alcohol. When the carbon that's attached to the hydroxyl group is attached to two other carbon atoms or to two other hydrocarbon chains and only one hydrogen, then we get what's called a secondary alcohol. And when the carbon that is attached to the hydroxyl is attached to three other carbon atoms or three hydrocarbon chains, we get what's called a tertiary alcohol. So the presence of that polar OH bond in the alcohol gives them characteristics that the parent alkanes don't have, right? Because the parent alkanes are completely nonpolar, whereas that OH bond allows alcohols to form hydrogen bonds. So what that means is the boiling point of an alcohol is much higher than that of the parent alkane because those hydrogen bonds will need to be broken. And just like the parent alkanes, as you add more carbon atoms, the boiling point will increase. Alcohols are soluble in water because they can form hydrogen bonds with water. As you get longer chains, the alcohols will also become soluble in nonpolar solvents because they have a large hydrocarbon portion. So molecules like this, where they've got a polar part and a nonpolar part, are called amphipathic. So longer chain alcohols are amphipathic molecules. Okay, our next functional group is the Alkoxy group. Okay, in this case, we have an oxygen that is single bonded to a carbon or a hydrocarbon chain on both sides. Okay, so this is just R prime indicating that it's a hydrocarbon chain, which may or may not be the same one as R. And so these are found in the ether group of hydrocarbon derivatives. So when you see an alkoxy group, that molecule is part of the ether group. So ethers don't contain any OH groups, and so they can't form hydrogen bonds like the alcohols, but they do have the CO bond, which is polar, so they can form dipole-dipole interactions. And so we know that a hydrogen bond is stronger than just a dipole-dipole interaction. So the boiling point of an ether is going to be lower than an alcohol with the same number of carbons. But the boiling point of an ether is going to be higher than just the hydrocarbon with the same number of carbons. Ethers are good solvents for organic reactions because they, like the alcohols, can interact with both polar and nonpolar substances. Okay, our next group is the Amino Group. This consists of a nitrogen single bonded to a carbon or a hydrocarbon chain on one side. And then over here on the other side, there may be hydrogens or there may be more carbon chains. Okay, recall nitrogen is always going to make 3 bonds, right? So it's going to be bonded to three things, at least one of which is going to be a hydrocarbon chain. So amino groups are found in the amine group of hydrocarbon derivatives. So amines can be thought of as an ammonia molecule, right, NH3, where one or more of the hydrogen atoms are replaced with alkyl groups. Okay, and again, we can subclassify amines like we could alcohols, although the classification is slightly different. It's not based on the carbon that's attached to the nitrogen, but rather on how many alkyl groups are attached to the nitrogen. So if we think of it as ammonia, where we're replacing the hydrogens with hydrocarbon chains, right? If we replace one of those hydrogens with a hydrocarbon chain, we get what's called a primary amine. If we replace 2 of those hydrogens with hydrocarbon chains, we get a secondary amine. And if we replace all 3 of them with hydrocarbons, we get a tertiary amine. So what does the presence of an amino group do to the molecule? So those NH bonds are very polar, just like OH bonds. So these molecules as well can form hydrogen bonds. However, the NH bonds are only in primary and secondary amines. So if we just go back here for a second, right? If we have a tertiary amine where the nitrogen is bonded to all carbons, there is no longer this polar NH bond. So the tertiary amines can't form hydrogen bonds. So what this means is that the primary and secondary amines have a higher boiling point than a tertiary amine with the same number of carbons. It's important when you're comparing boiling points of hydrocarbons and their derivatives that you're looking at ones that have the same number of carbons, because adding more carbons changes things too. So if you're not comparing the same number of carbons when you're looking at different molecules, then it's going to be hard to draw conclusions. Okay, the boiling point of those primary and secondary amines is also higher than ethers and alkanes of a similar size, because ethers and alkanes can't hydrogen bond. And so because they can form hydrogen bonds with water, they're soluble, and the smaller ones are very soluble. Okay, our next one is the Halide Group. So in this case, it's a halogen, which we're representing here by X. So any halogen, fluorine, chlorine, bromine, or iodine bonded to a hydrocarbon group. So these are found in the haloalkane group of hydrocarbon derivatives. So those haloalkanes, the smallest ones, are slightly soluble in water, but the remainder are insoluble due to their long hydrocarbon chain. They have a higher melting or boiling point compared to the alkane with the same number of carbon atoms. And the reason for that is you've taken, essentially what you do to create a haloalkane is you remove a hydrogen and you add a halogen, right? And the halogen atoms are much bigger than the hydrogen atoms. And so that larger atom with more electrons means an increase in London dispersion forces and therefore a slight increase in the melting and boiling points. Okay, so all the functional groups we've looked at so far have single bonds. So now we're going to look at functional groups with a double bond, in particular a C double bonded to an oxygen. So this group forms the basis for a series of different functional groups depending on what is attached on one side or both of this carbon, which is double bonded to an oxygen. So the first one is called the Formyl group. Okay, so in this Formyl group, this carbon that's double bonded to the oxygen is bonded to at least one hydrogen. Okay, so it must have one hydrogen here. And because it always has a hydrogen on one side, it's going to always be found at the end of a molecule. Right? So you can have a long hydrocarbon chain out this way, or you could just have a short one or just an H. But there definitely has to be an H on this side. So when you see a Formyl group, those are found in the aldehyde group of hydrocarbon derivatives. So molecules that contain Formyl groups are called aldehydes. So aldehydes contain that CO bond, double bond, and this is a polar bond, so they can form dipole-dipole interactions, but they can't form hydrogen bonds. So their boiling point is going to be lower than an alcohol containing the same number of carbons, but higher than a hydrocarbon. The small aldehydes are soluble in water, but as the hydrocarbon part gets longer, they're going to be less soluble. They're also good solvents for organic reactions because they can interact with both polar, with their CO bond, and nonpolar, with the hydrocarbon part. So hopefully as we go through the properties, you're starting to see some recurring themes, right? It's all about what intermolecular interactions they have, and in particular, whether they can hydrogen bond or not, that determines their melting and boiling point and their solubility in water. Okay, the next one is the Carbonyl Group, or Carbonyl Group. So in this situation, you've got this C double bond O, and it's bonded on both sides by a hydrocarbon chain. Okay, it's always found within the molecule. So there's got to be something on this side and a hydrocarbon chain on this side. It might just be one carbon, but it needs to be a carbon and not a hydrogen. So when you see this group, you know that the molecule is a ketone. So ketones are very similar to aldehydes. They've got that C double bond O, so they can form dipole-dipole interactions. Their boiling point is going to be lower than an alcohol, but higher than just the hydrocarbon chain with the same number of carbons. The small ones are soluble in water, but as the hydrocarbon chain length increases, they become less soluble. The next group is the Carboxyl Group. So this one has a hydroxyl group. So we've got like a carbon group or a carbonyl group and a hydroxyl group, which come together to make a carboxyl group. So in this case, this carbon that's double bonded to the oxygen is bonded on one side to a hydroxyl group. So again, this is always at the end of the molecule because this OH will end the molecule. The H can't bond anything else. The O can't bond anything else. So this is at the end. And then on the other side, we might have an H or might have a hydrocarbon chain. So this group is found in the carboxylic acid group of hydrocarbon derivatives. So carboxylic acids are very polar, right? They've got both, if I just pop back here, they have this polar bond, and then they also have this OH polar bond and the CO polar bond, right? So there's lots of polarity going on there. So they're able to form hydrogen bonds. Their boiling point is going to be higher than the hydrocarbon and the other derivatives, right? Because the carboxylic acid can form lots of different intermolecular interactions. The small ones are going to be soluble in water, but as the hydrocarbon part increases, it will become less soluble. So carboxylic acids are called that because they are indeed acids, right? They're weak acids. They will react with bases and they can conduct an electric current. Okay, the next one is the Ester group. So in this situation, the carbon that's double bonded to the oxygen is then bonded to an oxygen, which is then bonded to a hydrocarbon chain. Right, so if you think of the carboxylic acid, it had a hydrogen here. So to make an ester, you remove that hydrogen and then add a hydrocarbon chain. Okay, so this is going to be a little bit within the molecule. There could just be a hydrogen over here, but generally there'll be a longer carbon chain over here and then a carbon chain over here. And so in this case, the name is the same, which is handy. So the Ester group is found in the Ester group of hydrocarbon derivatives. So the esters still have that C double bond O group, and they also have that C single bond O, but they don't have the OH, so they can't form hydrogen bonds. So the boiling point of an ester is going to be lower than the corresponding alcohol or carboxylic acid. Again, the small ones are soluble in water, but as they get bigger, the solubility decreases. Esters are really volatile, so they'll become a gas, which allows them to create characteristic aromas, right? So they put molecules into the air and we can smell them. So this table I just thought was a little bit interesting. You'll understand more about the sides when we get to the naming, but these are all different scents that are created by an ester, right? So a banana scent is with a 2-methylpropyl and then a 4-carbon. So just lots of different scents that are made by esters. Okay, last one, the amide group. So in the amide group, the carbon that is double bonded to the oxygen is then bonded to a nitrogen. Okay, so it's kind of like we've taken the carbonyl group and added an amine group or an amino group, and we get the amide group. Okay, and they're found in the amide group of hydrocarbon derivatives. So just like the amines, they can also be classified according to the number of carbon atoms attached to the nitrogen. So if we look at the nitrogen, if it's only attached to this carbon, which is double bonded to O, that's the primary amide. If this nitrogen is also bonded to another carbon and one hydrogen, that's a secondary amide. And if this nitrogen is bonded on all 3 sides to carbon, we get a tertiary amide. So very similarly to the amines, right? The primary and secondary amides have at least one polar NH group, and they can form hydrogen bonds. And they all have the polar carbonyl group, so they can form dipole-dipole interactions. So the boiling point of the primary and secondary amides is going to be higher than the tertiary amide because it's able to form those hydrogen bonds. And the boiling point of primary and secondary amides will be higher than all the other hydrocarbon derivatives of a similar size. In particular, those primary amides, which have 2 NH bonds, and the polar carbonyl group can form a lot of intermolecular interactions and are going to have a fairly high boiling point. Okay, they can also form hydrogen bonds with water, and so the smaller amides are very water soluble. Okay, so let's just quickly run through all the functional groups that we've talked about. So we mentioned the alkenes and the alkynes, which you've seen before. Then the hydroxyl group, and its presence indicates that you have an alcohol molecule. Ether, which is found in the ether group of molecules. Amino group, found in the amines. Halide, so a halogen, so these are in the haloalkanes. The Formyl group, which is in the aldehydes. The Carbonyl group, found in ketones. The Carboxyl group, which is found in the carboxylic acids. the ester, which is found in esters, and finally the amide, which is found in the amide molecules. Okay, and one more summary. So just to compare their polarity of the different hydrocarbon derivatives, and then also the most polar would indicate the higher boiling point. So the amides are the most polar, followed by the carboxylic acids, then the alcohols. Okay, these can all form hydrogen bonds. Then the ketones and the aldehydes, which are very similar. Then the amines, the esters, the ethers, and finally the alkanes. Okay, so that's it. Those are all the functional groups we're going to be looking at and the hydrocarbon derivatives that you can find them in.